So next we have Professor Brian Plancher from because he's an incoming assistant professor from the Technical College, stopping this fall, where he will continue to lead the accessible and transformative of his lab. But now he's currently an assistant professor of computer science at the North College of Columbia University. And he's the co-chair of the Tiny Machine Learning Open Education Initiative and the IEEE grants technical committee on model-based optimization. The research is focused on optimizing robotic systems at all scales by developing, optimizing, implementing, and evaluating the next generation algorithms and edge computational system to algorithm hardware, software co-design. We also want to promote a responsible, sustainable, and accessible future. Basically,
Thanks. Good morning, everybody, or afternoon on the East Coast, or evening in Europe, or probably asleep in Asia. So yeah, today I want to talk to you about optimizing robotic systems at all scales, and I think you'll find that basically all of my ideas on good future directions align 100% with what was just said by Bishop. But coming at it from a slightly different angle, I'll take a little bit more of a computer architecture angle on this approach, and I'll blast through the robotics background to start because I think most people in the room agree with me that robots are cool. Robots can also mean, power grids or chemical plants or really anything that has this, sensing to actuation where we're dealing with some compute in the real world, right? And I think all of these systems show sort of a lot of promise for lots of things that are, good for the world, like disaster response, home health aid, autonomous cars, sort of name it. I would hope that the RSS audience is sort of aligned with me on that, but feel free to shout out, raise your hand if you disagree with me on any of this. But I think we all also know that, we still have a long way to go. The picture's about a year old, but Atlas is still falling on its head, sometimes when we try to do things. And for me, one major challenge here is just raw computational. Like I sort of like to take on the motivating challenge of sort of how do we enable the real-time edge deployment of lots of computationally bounded robotics algorithms, of which planning and control algorithms are sort of the core of my work and sort of the core of what we're focusing on today, but they're not the only one. Right? There's a lot of just compute challenges sort of at the edge. And some of you, and I don't know how many of you have sort of seen this chart, but this sort of blew my mind during my PhD, which is that I sort of just assumed we were still living on this curve where, processor speeds just got twice as fast every year, computers just got twice as fast. I hate to break it to you if you haven't seen this, that is absolutely not the case. Since about 2005, we've sort of been at stagnant clock rates of a couple of gigahertz. And the computer architects, they're working hard. The computers are still actually getting a little bit more performant. The actual performance curves are still increasing, but less so. And what you've seen instead, and sort of the focus of this workshop today, is parallelism. Right? We've seen the number of cores sort of explode on CPUs. But it's not just CPUs. I think most people today are actually talking about GPUs. So I wanted to, give you a little comparison here of how I like to think about it from an architecture standpoint. And when I like to look at the architecture of like a multi-core CPU versus the GPU, I like to just sort of think about it as having like some amount of math, which is like the green blocks, some amount of memory, which is like the yellow blocks, and some amount of sophistication in their control logic, handling branching, prefetching, doing lots of cool complex things. And your standard multi-core CPU is explicitly designed to do everything at all. So it's sort of designed to have a nice balance of all things. It's a nice big RAMs and other memories for sitting down there. Your GPU looks quite different, right? And many of you may sort of be aware of this, but your GPU has a lot more compute. But now, instead of having sort of like 4 cores, we now have sort of these rows as actually the physical hardware cores on a GPU. And a GPU really, like, while you might think of it as being able to do millions of threads, really it's actually like tens to hundreds of physical cores that each have sort of hundreds to like 1,000 compute units in them. And so that's sort of how your GPU works. And we got a lot more compute here at the expense of a lot less cache and a lot less sophisticated control. And so your GPUs are quite good at things that are sort of naively parallel, but we make this trade-off of a sort of more rigid computational model. If you try to ask your GPU to do just anything in parallel, it's not always going to be good. So like, while I'm here to say I believe very strongly in parallel computing, be careful, your algorithm may not sort of naively parallelize unless it is nice for parallel, unless you can actually launch things that are. So I want to leave that as sort of some quick like computer architecture context for all of you. What is the solution to doing this? And in my opinion, very biased opinion, it's algorithm, hardware, software, code. And to me, that sort of means I want to think about like whatever computer architecture I'm running, whether it's CPU, GPU, CPU, FPGA, microcontroller, you name it. I want to think about sort of the design of that architecture, what it's good at, what it's bad at. I want to think about sort of the algorithm flow, what my algorithms are good at. And I want to think about it sort of in the context of the application domain that we're playing in robotics and the sort of real-time constraints that we're handling, right? And so depending on your application, your power budget, your size of your robot, your whatever, you might choose a different piece of computer hardware, which means you might want to choose different algorithms to run on your robot. And I think this sort of co-design process is cool, fun, powerful, and important. And so I wanted to give you a little case study on nonlinear model predictive control. I'll talk mostly about scaling out on a GPU, but I will mention briefly that you can use this sort of paradigm to also compress things down. Right? And I know we're talking about parallelism today, but sort of taking this lens of the computer architecture, the computer hardware matters, can help you also in a lot of other ways. So that's sort of my like high-level approach to robotics, motivation. Let's do a quick background on MPC, although we already covered a little bit of that earlier, and I'll give you sort of so I like to think of MPC at a high level as saying we're going to continuously be recomputing trajectories towards the goal, right? You saw in Evangel's little gifts there, right? The lines keep shooting out as the robot's moving, and we're sort of moving towards the goal, right? And the reason we like this, if you haven't seen MPC as much before, is that you will never exactly execute your plan. I don't care how good your simulator is. I don't care how good your sensing is. Like, there is noise in the world. There is a little bump there. There's a little dirt in your motor. You won't be perfect. And so we want to sort of recompute and execute and recompute and execute. And so we want to think about how do we compute this optimization process fast online. So what are we solving? Well, we're solving an optimization problem that often is sort of set up as minimizing some cost function over time. And this could be something like distance to goal, squared torques, and maybe there's a batch of them. And we want to obey physics, and we want to I don't know, don't run into the wall, don't go through torque limits, stuff like that. Right? And this is a very general, non-convex, nonlinear optimization problem. And there are a number of ways to solve this, right? There's, zeroth order optimization, first order optimization, second order optimization, lots of other different ways you can do it. Today, I'll take the approach of saying, what if we wanted to use sort of like a more classical, compute an actual gradient, do gradient descent type method approach? How might we split out the GPU? Right? This is the kind of algorithm class that maybe isn't naturally as portable, but I want to show you that it can be done. Right? So what are we going to do? We're going to solve successive convex optimization. That is, we're basically going to say, this problem is too hard. I can't solve it exactly. It's way too nonlinear and non-convex. So what I'm going to do is I'm going to locally compute some quadratic and linear approximations to turn this into a QP. Once I've done that, I just have to, take my little bowl, go downhill, form a new little bowl, go downhill, form a new little bowl, go down. Now, sometimes when we're doing this, we're going to end up in a case where our approximation is going to send us to something that's actually worse than where we started. And so this is where sort of a line search or a trust region or something like that usually comes into play. If we're doing a line search, we'll basically sort of back off the update. And we'll say, hey, I'm just going to do a little bit less. And eventually this will sort of converge back to where you started. And if you're totally at the bottom, you'll probably exit saying, hey, I've converged to a solution. And this is sort of the idea of this successive convex optimization, which powers a lot of optimizers that you probably use, whether you know it or not. Now, this approach works quite well, and it's still too slow. Right? And if you look at a lot of the talks that, like, I don't know, Scott and Robin and Tuan have sort of been giving over the years, they spent a lot of time, tuning the living daylights out of their optimizer to try to get Atlas to do all the amazing things that it does, and yet it's still often too slow. So that's my motivation to say, let's put it on. Let's think about sort of scaling this up. Now, before I continue to just sort of plow through very fast, any questions so far?
I have one question.
Yeah.
Are you talking about single shooting or multi-shooting?
I'm gonna do full QP solves.
But
I guess
does this involve forward propagation of
I'm not gonna do ILQ or GDP. I'm gonna do like the solve with QP.
including your dynamics as
Including my
quality
dynamics.
constraint?
Yeah, as a quality constraint. Yeah. And I'll set that one up. I've done it as a single shooting and a little bit of multiple shooting too, and we can talk more about that later. GDP, you can only multiple shoot it so much before you start to get into some. Yeah. Anyway, longer conversation. Yeah. Okay. So everybody else good? Awesome. Now that I've flipped back and forth 6 times and given the people on Zoom a headache. Okay, so what are we trying to do? We're trying to co-design our solver to exploit the SIMD parallelism on a GPU, the structured sparsity and design of this optimal control problem, and sort of working over all the algorithmic objects. And to that point, single shooting, multiple shooting, SDK, all this kind of. One thing that I've sort of realized is that this sort of successive convex optimization approach is really bottlenecked by 2 things in a parallel computation world. It's the computation of a lot of physics gradients, and it's the solving of a linear system or doing that forward-backward shooting thing. And so really what we needed to do was figure out how to accelerate these 2. Now, I don't have enough time to go into sort of all of it. On the physics gradient side, this is a little bit older work. We did some algorithm refactoring and code generation to develop some efficient physics gradients, noting that in these optimal control problems, I only want tens to hundreds of computations if I'm solving, say, 1. And so therefore, given that GPU architecture has tens to hundreds of cores, I actually want to distribute each computation to a core and then thread within the computation, not just across the computation, if I want as much speed as possible. So that was sort of our grid library. If you believe me and take that as existing, I have now officially developed a QP. And so the question I wanted to, again, talk about briefly, because we just don't have enough time to go into super details, how do we solve this? And it turns out, just like your standard single-dimensional quadratic problem, if you want to minimize a quadratic problem, you end up with solving some sort of linear system, right? Take a derivative, set it equal to 0, haha, we have to solve things. And so what we're bottlenecked by here is solving this particular linear system. Now, there are a lot of ways to do it. There's those multiple shooting, single shooting, forward-backward propagation thing. We can also try to just literally solve this. OSQP will factorize this and try to just solve it exactly. On a GPU, that's not great. The algorithms that the GPU literature would tell you to use are these iterative methods, like preconditioned conjugate gradient, and I'll show you in a second why they're more parallel friendly. But before we can use those, we run into a problem, which is that this requires a symmetric, positive, like semi-definite system and a good numerical preconditioner. This is a terribly conditioned indefinite system because of this like big 0 here. We can add some regularization and stuff to try to get it where we want. The approach that we did actually was just a little linear algebra trick where we actually formed what's called the Fisher complement. Now, the reason we did that is 1, this thing is PSD, but also it's block tridiagonal. And what's really nice about that is that once we've generated this very specific structured sparsity, we can implement a structure exploiting solver that can actually map to the GPU a lot better. And the reason we can do that is this is sort of, don't worry about the details, the naive conjugate gradient algorithm. And really what we're doing here is a lot of matrix vector products and sort of vector reduction. And if we have this tridiagonal structure, we're just sort of slamming matrix vector products of this vector down here, we can basically put each block row into one of those little caches and only have to do a little bit of sharing across them first. And so this can enable us to do very parallel dot products, very little sharing, and end up with pretty efficient conjugate gradient solvers on the GPU. Now, this doesn't scale infinitely because I'm using the GPU in a specific way, but it scales quite nicely to like a trajectory optimization size problem. So lots more details, but basically that's the trick in PCG solver. The next step becomes, okay, we now need a good parallel preconditioner. And for those of you that haven't seen preconditioning before, basically if you have some matrix AX equals B, you can solve, if you have some like magical matrix phi, that's roughly A, but easy to invert, we can instead solve the problem phi inverse A, X equals phi inverse B. And the reason we want to do that is because basically this is kind of identity, so we're sort of done. So if you come up with a really good preconditioner, you kind of jump to the solution. And also it makes the numerical conditioning nice, the math doesn't explode, lots of things like that. Again, I don't really have time to go into the details, but we did some theory work and we figured out how to design a block tridiagonal preconditioner that's quite nice for this specific kind of problem, which then it goes through this staircase. And therefore, we again have that structure sparsity that we want, and we actually have this parallel computability and all these sorts of things in that as well. So we put that all together, and let's run like a 5-point pick and place sort of task and try to see how fast we're going and how well we can scale. And so I want to compare this to QDLDL, which is the linear system solver inside of OSQP, right? Which, as you increase the size of your problem, it takes longer time. Of course it does. It's doing a factorization. It like literally has to compute more math. What we find is that we can actually scale a lot better, right? By leveraging this sort of parallelism. But what was interesting to me was not the like raw number speed up. It was more actually the distribution of solve times. And so what I found kind of interesting, so the CPU is doing this deterministic algorithm. And so it takes a deterministic amount of time. Here's a CDF, this is time, and this is the percentage of solves. What we can generate is a solver that's both way faster and much slower at the same time. So what's going on here? So we thought about this a bunch, and it turns out that this particular task that we sort of set up somewhat randomly is actually kind of interesting in this case because it's very warm started along these big, nice curves, and it's very cold started every time it stops and changes direction. And so sort of what's happening is that these PCG solvers like kind of iterate around until you get to under some tolerance. And so if we're warm started, we actually do very few loops here, and we kind of just exit because we're also really close to the solution. If we're cold started, we might have to crank for a while, right? And that's generating this variability. And so we can actually sort of start to tune that exit tolerance and shift this distribution mass more and more to the left. And we can end up with something that, you know, in this particular case, we were 10 times faster, 65% of the time, only 2.5 times slower. In worst case, like doing quite well. And we've got some new work we're trying to work on right now, try to see if we can just sort of like cut off this distribution, you know, and shift it more over still. But I think this was sort of an interesting look for me in that like sometimes the average solve time doesn't matter as much maybe as the distribution. And it was giving me a different look into how to think about the research, which I found kind of fun. I'm going to totally run out of time, so I'll just like keep clicking. But basically, so we put this at the core, we tack on, you know, those fast gradients from before, and then we do this line search super parallel because we can just run all the line searches in parallel. You know, kind of like how MPPI is rolling out a bunch of trajectories. We'll just roll out a bunch for the line search. We put that all together. This was the MPC GPU paper at ICRA. And so here, what I want to show you is what we end up with. So here I'm saying I want to guarantee some control rate. So once I have, you know, 1 millisecond, I must send my current solution. Once I have 4 milliseconds, I must send my current solution. I'm going to change the time horizon. If you put sort of like a 1 anywhere in here, this would be like a real-time iteration scheme that I know many people in this room have used such things before. Do 1 QP solve, send it right back to the robot. If we restrict to a slower control rate or less knot points, we can do a lot more iterations, right? We can run this a lot faster because it just scales quite well. And we can actually scale it all the way up to 512 knot points, 1 kilohertz through the full solve there, which is pretty big and pretty fast, which I was pretty happy with this. Now, here's where it becomes basically your talk from before. What if you don't need that fast of a solve or that long of a trajectory? Maybe we should batch things, right? And this is where I'm also thinking that there's some sort of interplay here between sampling and optimization. Coming from the more optimization, I want to do tens of, you know, optimization solves here. I don't think I have to sort of say why. We've sort of said that this could be a good thing. There's a number of reasons it could be useful for learning, for hyperparameters, unknown disturbances, integer modes, something like that. I'll show you one quick little demo that we're working on that I thought was kind of nice. Here, basically, I didn't tell the robot that we're yanking it with this heavy weight that kind of moves around, and it's just like trying to hit its points, and it's doing okay. On this one, what we did is we sort of said, assume there might be an unknown disturbance. Let me run a batch of 8 to try to like triangulate where the disturbance is. So I don't have force torque sensors on. I've assumed we're sort of running blind. But if we just have even just like 8 solves, we can very quickly sort of understand instantaneously roughly what that disturbance is. And we have these 8 solves going that are sort of trying to handle it, which is letting us adapt a lot better online to that sort of thing. So maybe it's somewhat contrived demo, but just sort of showing this like sampling over gradient optimization. Yeah, I'm totally with you. It totally seems like a very cool thing. I don't know the right way to set it up. I'm excited to sort of explore this too. And what are we doing next? You know, we're generalizing this. We'd like to open source this stuff for all of you. We're improving our preconditioning. We're doing some risk sensitivity work with TRI. We've got some support from NSF, but also I want to do that accelerated learning thing that you're talking about too, right? I think we can batch for learning. I think this could be really interesting. And I want to scale up that multi-contact. I want to do context implicit locomotion because I think we can do it in real time, which I think would be really, really fun. So that, I think I have like 1 minute left. So let me just do one quick thing on this. You can also compress this down. We did this with the tiny NPC thing. Long story short, partial caching, partial online, doing some fun games with the algorithm, knowing that we have literally no memory and very little compute. We can play some sort of games here too. We can get it to run at about 500 hertz on the drone, and we can do conic constraints. We can do real-time obstacle avoidance, and we have some new work that'll be at IRS. We can actually we've improved the solver a bit, and we can do disturbance rejection from some wind. So 1,000 people to thank. I've been at Barnard running with this. All work is mostly undergrads and master students. They're awesome. There's all their names. A bunch of them are starting PhDs. A bunch of them will. You should hire them. They're great. And I'll be at Dartmouth, and I will be hiring PhD students. So if you think this idea of algorithm hardware software co-design is cool, or people who might, let me know. I am definitely over time. I will shut up now. Cool.
Any question from the audience? We have time for one.
But bug me. Okay.
Actually, I have one question.
Okay.
So when you solve the linear system in parallel, so you have to send some shared information between different threads, right?
Yeah.
How much of the overhead is there? And because I think it depends on how small you divide that matrix into several separate.
So in general, when I'm using the GPU, I like to think of sort of 3 levels of memory speeds in a sense. So they have these very small cache memories, and anything you keep in there is roughly free between the threads on that block. And you're guaranteed that each block will run on its own, on the same core. So that's why that's it's not free, but it's very fast. So let's just treat it as mostly free from a algorithmic standpoint. When you want to transfer the memory between the blocks, in which we're doing between the block rows, there's a little bit of overhead because usually you have to go through RAM and you have to synchronize the GPU, and that has some overheads. So it's not free. It's not terrible, but it does really hurt your performance. And so we were really trying to figure out how we could design it to minimize that in general. And then the thing that kills you is if you have to go to the CPU and back. So unless you're on a Jetson or something with a shared RAM, that IO through the IO bus is terrible. And so when we did first the original dynamic stuff, we were getting 7 to 10x speedups. But then if I tried to ship all those gradients back to the CPU, I would go to 1.5, 2x speedups. It would crush most of the speedups.
And how do you synchronize? Different thread will return different solution for the share component of the matrix. So how do you synchronize them?
So we do a lot of work trying to think about making sure there aren't race conditions, and then the GPU actually, if you write it in CUDA, for example, there's literally a line that you can do that's called sync threads, and it will synchronize threads. So basically you're all right, everybody do some work, dump it into memory and sync. Everybody do some work, dump it into memory and sync. But I will say that I am currently trying to think about this JAX, Warp, all these other sort of more high productive programming environments, because CUDA takes a really long time to write all the code. And that was good when it was me by myself during COVID in my attic, during my PhD. But now that we're trying to scale up and add more features, it takes a while. Yeah.
Well, thank you for the great talk. Let's thank the speaker.